Okay, so last section of 12A, then I will finish 12B today and post it, and we are done as far as enrichment in equilibrium concepts as far as an enrichment activity. So one thing you want to understand about an equilibrium is what a catalyst does to it. And please understand that a catalyst equally increases both the forward and reverse reaction. So it does not change the value of K equilibrium. It does not make it more or less reactant or product favored. A catalyst just gets you to those equilibrium, non-changing pressure or concentration equilibrium values. It just gets you there faster. And a catalyst does, again, does that through providing that alternative pathway that has a lower energy of activation. So finally, let's talk about Le Chatelier and what Le Chatelier does or allows us to predict. And Le Chatelier says that if you disturb, or as we talked about in the first section of this unit, poke an equilibrium, it will respond. On the AP test, there are 3 ways that you will need to predict, or 3 ways you can poke or disturb an equilibrium, and you should be able to predict what that will do to the equilibrium reaction. The first is changing temperature. Please note that the value of K equilibrium always changes with temperature change. If you increase the temperature of a container at which an equilibrium reaction is going on, if you increase the temperature, the equilibrium reaction that's occurring inside the container will shift in the direction that will use up that that heat that was added to increase the temperature. So it will move in the endothermic direction. Again, depending, endo could be forward or reverse. So you want to remember endothermic direction if you increase the temperature, which should make sense because if you're increasing temperature, that means you added heat to the equilibrium system. And Le Chatelier says the reaction will respond to minimize that stress. So the reaction will respond in an endothermic direction to use up that heat that you added. In contrast, if you decrease temperature in a reaction vessel where an equilibrium is going on, the equilibrium will respond. And how would you decrease the temperature in that reaction vessel? Probably by removing heat. So the equilibrium expression will respond in a direction that is exothermic in an effort to replace that heat that was removed to decrease the temperature of the reaction vessel. So the key point here is you increase the temperature of an equilibrium reaction, the equilibrium reaction will respond by moving in the endothermic direction. If you decrease the temperature, which was done by removing heat from the system, the reaction will respond in a direction to replace that heat, or the exothermic direction. Another way you can disturb an equilibrium is by changing the concentration of a reactant or product. Remember that change in concentration could also result in a change of pressure of a reactant or product. And then another way is to change the volume of a container that holds an equilibrium reaction that's occurring. If you increase the container volume, think about it, if you increase container volume, the pressure inside will go down because the particles won't be hitting the sides as much. And how would we respond, or would the reaction respond to the pressure going down? It would want to go in a direction that would increase pressure in response. So if you increase the volume of a container, the reaction will shift in a direction that you see the most moles of gas. That could be forward or reverse, just depends on where you see the most moles. Are they a reactant or a product? If you decrease container volume, please note that the pressure of the system goes up. And so in response, an equilibrium will want to move in a direction where it can lower pressure, so it will move in a direction where there's the smallest moles of gas. That might mean moving in the forward direction or the reverse. More on that in a second. If the reaction has equal moles of gaseous reactants and products, changing the volume of the container will do nothing to change the equilibrium. And changing pressure caused by changing the pressure that by adding a non-reactive noble gas will have no impact on the equilibrium as well, which should make sense to you, because to have an impact, that gas that would have to be added would actually have to act as a reactant or product, and noble gases don't react. Le Chatelier's principle states that if a change or a stress is imposed on a system, the position of the equilibrium will shift in a direction that will minimize that change of the stress. Please remember that, well, let's just jump right into it, the effect of temperature on an equilibrium composition. You can make a qualitative prediction on the effect on a temperature change on the composition of an equilibrium if you know the endo and exothermic direction of the reaction. So, all right, so let's take a look. So we have our reaction here, A and B going to C and D. It's endothermic in the forward direction, because notice heat is a reactant in the forward direction, but in the reverse direction, this would be an exothermic reaction. Please note at lower temperatures, an equilibrium will move in the direction that produces heat, so it will move in the exothermic direction. So if we took this reaction and it was occurring inside a container, a sealed system inside a container, and we lowered the temperature inside the container, it's going to move in a direction that would produce heat, so it would move in the reverse direction. If this reaction was occurring in this container and we increase the temperature of this container, it would want to move in a direction to minimize that added heat, which would mean it would move in the forward direction or the endothermic direction. So bottom line is at lower temperatures, the reaction above, so at lower temperatures, the reaction above will move in the direction that makes heat, or the reverse direction, to reestablish an equilibrium. And if it moves in the reverse direction, remember, it will release heat to minimize the stress. And the magnitude, so notice if we go in reverse, what's going to happen? The new K, so K new, if we move in reverse, the reactants are going to get bigger, and the products have to get smaller. So essentially, bottom line in this case, our denominator is getting bigger, so our new value of K is smaller than it originally was. What's interesting is if you bring the temperature back to where it was originally, your value of K will go back to its original value. So notice here at higher temperatures, the reaction will want to move in a direction that gets rid of this heat that was added to get to the higher temperatures. So it will move in the forward or endothermic direction to reestablish an equilibrium, thereby absorbing heat to minimize that stress. And notice if we go in the forward direction, what's going to happen to our new value of K? It's going to get bigger, because if we go for the amount of C and D will remain higher, and A and B will have decreased. So K gets larger in this case. Now let's take a different example. Notice here our equilibrium in the forward direction is exo, which means in the reverse direction it's endo. Now think about this again. At lower temperatures, you get lower temperatures by removing heat. The reaction's going to want to produce heat or move in the exothermic direction. So at lower temperatures, the exothermic direction is forward to reestablish equilibrium, thereby releasing heat to minimize the stress. And what's going to happen to our new value of K again? if it moves forward, what's going to happen? In this case, C and D are going to go up in molarity or pressure, and A and B have to go down. And so therefore, our new K in this case would be larger. At higher temperatures, the same reaction would want to go in a direction that uses heat, or the endothermic direction. So at higher temperatures, this one would go in the reverse direction to reestablish equilibrium, thereby absorbing heat to minimize the stress. And what will happen to KC? KC will get, well, let's see, it's going to go higher temperature, it's going to go in the reverse. So what's going to happen to our new value of K at the new higher temperature? If it goes in reverse, A and B are going to go up in molarity or pressure. C and D go down. And so this is going to decrease. So, to summarize, when the temperature of a system at equilibrium increases, the equilibrium shifts in the direction that uses heat as a reactant. And when temperature system decreases, the equilibrium will shift in the exothermic direction, or that releases. It's really important to note, though, if we go back to our original temperature after increasing or decreasing it, the original K will be restored. Remember, it's only changing temperature that will permanently change the value of K until the original temperature's restored. So, how would this look like on a graph? So notice in our picture here, we have a reaction of A2 and B2 going to AB2. Notice that B2 here, to get to equilibrium, went down 2 units, or 2 of these. B2 went down 4. That's why B2 has a stoichiometry of twice as big. Notice we reach equilibrium, it looks like right about 5 minutes. Okay. And then notice at some time out here at 10 minutes something happened. And notice at 10 minutes it looks like the reaction, well, if we look what's happening here, the amount of AB went up and the amount of A2 and B2 went down. So it had to have definitely been shifting forward. And let's say we increase temperature here. So if we increase temperature at this point right here, we increase the temperature. We know that that increased temperature caused the reaction to go forward because our products, our AB2 went up and our reactants went down. And as a result, we know that the forward reaction must be endothermic. So we know that this reaction must have been heat plus A2 gas plus 2B2 gas doing 2AB2 gas. Okay. And notice in this case the new value of K, or K new, is probably going to be larger than the original K value because we have more product and less reactant. So it's definitely shifted in the product's favor. Let's look at the next example, CO2 decomposing to CO and O2. Notice what's happening here at some time here. Look, so we're at equilibrium probably here, so we have an equilibrium value here. And then notice CO, we stress something here. So we stress the equilibrium, and we know that because the equilibrium values that were established are changing. Notice our CO, our product, went up, and notice our O2, our CO2 went up. So that's our reactant went up, and our two products went down. So it had to have been going in the reverse direction. And we decrease temperature here. If we decrease temperature here, notice that it would have to go in the direction that produced heat. So the reaction moved in reverse. And we know, again, we decrease temperature, it's going to move in the exothermic direction. So that tells me that heat, when we lowered temperature, it did go in reverse, so that the heat must have been a reactant, because when we lower temperature, it's going to go in the exothermic direction. Another way is to use a visual observation. Notice in this given equation here, it's an equilibrium, double arrow. And notice you have two options here. The reaction could be exothermic as written, or it could be endothermic as written. Notice exothermic as written, heat's a product. Endothermic as written, heat as a reactant. Now notice as temperature went up, it got more darker red, and C is red. So at higher temperatures, it should be going in the endothermic direction. And notice it got more red at higher temperatures. And therefore this has to be the correct reaction, because at higher temperatures it got more red and the product C is more red. So there's another way to visualize what's going on in that equilibrium. So bottom line is, at higher temperatures a reaction goes in the endothermic direction to reestablish the new equilibrium. If, this is going back to that previous question, notice it became more red as temperature went up. So that said that the reaction had to be endothermic as written, as we just talked about. Some practice on on the bottom of page 45. Let's talk about the addition or removal of a reactant or product. Again, an equilibrium will respond when you add or remove reactant or product, but K value will not change. Only temperature will change it permanently. All right, so if we have our reaction here, if we add a reactant, notice that means that we're no longer at equilibrium. So if we add a reactant, it becomes too big, which means Q, when we think about Q is going to now be smaller than K because we're adding extra reactant. So the reaction will proceed forward until now enough product is made and enough reactant is used up to where Q now re-equilibrates or re-equals K equilibrium. So if we add reactant, the reactant molarities or pressures will decrease as the reaction moves forward to get back to equilibrium, and the product concentrations or pressures will increase. If a reactant is removed, so let's say we remove a reactant, so now all of a sudden this gets smaller, our Q becomes bigger than K, and so if we remove some reactant, it's going to want to go in reverse until we replenish some of the the reactant that was removed. So if we remove some reactant, the reactants will want to increase. And remember, where do we get these? Increase. Let's try that again. And if we move in reverse, the reactants will increase. Well, where do those reactants come from? The products. So the products will decrease. Graphical observing of this, notice what's happening here at their stress time. Only one thing changed, and it changed quickly, and that was the molarity of NO2. So that would indicate that NO2 here was probably added. So what would happen if we add more N2? The reaction will shift to the right. Notice vertical line there. the reaction will shift to the right. The amount of NO2 will go down. The N2O4 will go up, and that will occur until. So notice that will occur until the K is back to what it started at. So again, if we look here, when we add the N2, what's going to happen here is Q. So we're going to add NO2. So now we're going to go NO2. So we're going to add in reactant NO2. And it's going to be product N2O4. This is going to be too big. So what's going to happen is Q is going to be smaller than K. And so the reaction is going to have to, the stress causes reaction to move forward. And we know that because notice, after that happens, the product molarities go up and that NO2 goes back down. And notice here, so here's our K original. Here, our Q has gotten smaller and K new. These two right here, after equilibrium is reestablished, are the same. And they become the same because after we added NO2, some of that NO2 will shift and become, or react and become N2O4 until Q equals K. Now if we look at this example, kind of another graphic example, notice what's happening here. It looks like only one change and it happens really quickly. So it looks like NH3 is removed. And notice NH3 is a product. So what's going to happen at this stress time? So what happens at the stress time, Q, so products over reactants. So we're going to get NH3 is going to go down, and N2 and H2. So that ratio is going to go down, and so we're going to need to shift forward. And we know we're shifting forward because after you remove that ammonia, we're going to have to replace it. And notice N2 is going down forward as it moves forward to replace the ammonia, and H2 moves down. Please note that our original K and our K of the new equilibrium will be the exact same values once equilibrium is reestablished. Reaction shifts or moves forward to reestablish equilibrium. Again, once it's done, the original K you had will equal the new one. So, effective volume changes. Remember, when you stress an equilibrium by decreasing volume, the system's pressure will go up. Le Chatelier says an equilibrium will go to minimize that stress, so it wants to shift in a direction that will make pressure go down. So it will shift to the side of the reaction with the least number of moles of gas particles. But remember, K remains constant because the only thing that's going to change K is going to be a change in temperature. If you stress an equilibrium by having an equilibrium in a container and you make the volume of the container larger, the pressure inside the container will go down, so the reaction will shift either forward or reverse or to the side of the reaction that has the highest number of gas particles. If both sides of an equilibrium have the same number of moles of gas particles, changing volume will not change the equilibrium. The other thing they will often throw at you on an AP exam is they will talk about changing the pressure of the system by adding an inert, non-reactive gas like a noble gas, and that will do nothing to shift the equilibrium. So here's a kind of an outline that comes all of your Le Chatelier principles together. Please notice that it's only changing the equilibrium value if you change temperature. changing or adding or removing a reactant or product, or changing pressure by changing volume of your reaction container will initially change Q. You'll no longer be at equilibrium, but the equilibrium will respond, and eventually the equilibrium value will be reestablished. So let's take a quick look here. We have our reaction, and delta H is negative, which tells us exothermic, so that would be plus heat. Okay, and it says what would happen if you decrease the volume of the system. If you decrease volume of this equilibrium system, so if this was in a piston, what they're saying is we have our equilibrium occurring in here, and if we decrease the volume of our system, of our equilibrium occurring in here, if we decrease the volume, it would mean that pressure would go up. If pressure goes up, the only way to, again, Le Chatelier says that equilibrium response is to decrease pressure. So it will move in a direction where there's the least moles of gas. Notice in this reaction, 3 moles of gaseous reactants, 2 moles of gaseous products. So this direction will shift to a direction that will minimize pressure, which will be the forward direction where there's less moles of gas. Equilibrium constant, no change, because only temperature will change that. And what will happen to the moles of SO3 if we go forward? Moles SO3 will increase. Adding oxygen, so now we're going to add oxygen, which is a reactant. Well, what that tells us is if we add a reactant, we need to, Le Chatelier says this will respond in a direction to lower that oxygen, which would mean it would need to go in the forward direction and use up some of the oxygen going in the forward direction. But remember, it takes some SO2 with it when that happens, and that adjusts the equilibrium constant back down so that there's ultimately no change in the equilibrium constant. In adding oxygen and shifting the reaction to the right, you will also increase the SO3. Raising the temperature, if you increase temperature, reaction will proceed in the endothermic direction. What's the endothermic direction here? Endothermic, because heat's a product, endo would be reverse in this equilibrium. So increased temperature endo, which is reverse. That means the equilibrium constant. Now remember, the equilibrium constant, that means that if it goes in reverse, the new K would be, if we go in reverse, less products will go down when it goes in reverse, and the reactants will go up, whether it's pressure or molarity, and so the value of K will be decrease. Again, if it's going in reverse, that's going to mean that moles SO3 decrease, because SO3 is a product. Catalyst, remember, adding a catalyst or removing a catalyst will have no effect at an equilibrium. It'll have no effect on K. And it'll have no effect on all that removing or adding a catalyst will do is change how long it takes to establish your equilibrium, not where the equilibrium is at that point. Okay, so that's it. If you would please work on the remainder of the notes. I will post the answer key to the notes. I will post that key by the end of the day, or for sure by tomorrow morning probably I will post that. Thank you for taking time to do this. Again, I'm just trying to do my best to support you guys. And if you have questions, please email me. And I thank you for your time.